So, so we're coming to the end of how we described the finite dimensional Hilbert spaces. So, before having a recourse to finite dimensional Hilbert spaces to infinite dimensional Hilbert spaces, we'll have a how we can formulate something called, which you might be aware in your earlier. You might be aware if you are students of physics or in general also mathematics, also something called Hilbert spaces. So Hilbert spaces are normally studied. We say they are infinite dimensional Hilbert spaces, infinite dimensional vector spaces. But since we have been studying finite dimensional vector spaces. So how do we see them in that context? So finite dimensional inner product spaces. So if how can study Hilbert spaces as a generalization of finite dimensional Hilbert spaces? Finite dimensional vector spaces. That's one. So we would say Hilbert spaces are infinite dimensional vector spaces. We can say how we can study Hilbert spaces as generalization of finite dimensional vector spaces. And if we have a simple definition of Hilbert space, which is Hilbert space can be defined as it's an inner product space modulo or what I should say modulo that this one with one extra condition, with one extra condition. So the condition is the condition is something called completeness. So what do we mean by that? So we know in finite dimensional cases, vector spaces, the condition of completeness is automatically satisfied in that sense. But for example, if we just extend it to infinite dimensional vector spaces, or if we, how can we define the sequences? For example, in the simplest cases, uh, if you want to generalize this definition, when we try to have and the boundedness properties. So how we define a sequence? In the previous class, how we defined a sequence, how we define the convergence of a linear transformation, that would be the proper way, and how we defined, for example, so how we define the convergence properties of these sequences. And for example, if we have an infinite dimensional case, if n and m go to infinity, infinity, so this will go to zero, as we have been doing the things in the previous classes. So here is the problem. But the problem arises, for example, when x n. So we could normally we may fix this one, or we may not fix it. So if we fix it with some with the boundedness associated with this thing, so then we can also define this convergence properties accordingly. But for infinite dimensional case, you cannot, if we fix this thing, it may not, there is no vector for which there is no vector for which this can be defined infinite dimensional case. For finite dimensions, we can just fix the since so intrinsic in it comes the notion of whether it's bounded or unbounded. The point is that, for example, so what how do we circumvent the problem? We just go in an inverted way. Inverted way is that we'll say that the only effective way is to assume the opposite. So what's the opposite? The opposite is that Hilbert space is complete inner product space. So, even though this can extend to infinity, this space is infinite dimension, but the point is it's still complete, and it's an inner product space which can be complete in order to circumvent this thing. So, if you assume that if it's complete to circumvent this this problem, so we can always say that the concept of this concept of Hilbert space is need some additional restrictions to assume if it's an infinite dimensional vector space, or the additional conditions is that it's complete in that sense to begin with. If we have to just circumvent to do away with these problems, so we define Hilbert space with some additional assumptions or additional conditions, and the purpose of which is to limit the size of the space above or below in which it's defined. And for this, the space has to be infinite dimensional, and you can use another word, it's also separable. So that makes it more intuitively visualizable. That's the thing. So in literature, modern literature, there may be more conditions which may be added to it, but for the simplest cases, this will suffice for us in that sense. How can we define Hilbert space? That it's complete inner product space, and it's infinite dimensional as well as separable. Yes. Now the point is, so in mathematical lore or in mathematical literature, there can be one or two more ways of how we can further define Hilbert spaces. So if we have a couple of them, for example, we can just have a couple of them. So we say that space of polynomials with inner product defined as space of polynomials with inner product defined like this is not complete. Is not complete. So if it's not complete, so the space of Hilbert space it is complete. So if we define it in some interval, so it should be complete. So there is a particular theorem which will not prove but will only state in this context, Rees-Fisher theorem is manufactured out of the set of those functions for which Hilbert space is manufactured. So this is the thing. Hilbert space is manufactured in the sense that the way we have used gram, if the gram shift orthogonalization condition, previously also we studied how can I construct this since spaces to make it more complete, or we can construct things. So in the same sense, we can construct or manufacture a Hilbert space, to use a cruder term, out of set of functions for which this thing xt square dt is less than infinity, in the sense of the Lebesgue integration, in the sense of Lebesgue integration. So maybe we are taking recourse to Lebesgue integration, which we will not have studied, but since as a mnemonics, maybe you might in the taking future course in some functional analysis, so we can also define Hilbert space in this sense, in the sense of the Lebesgue integration. With a formally same definition of another product as that of polynomials. Another popular definition one, so we can say that Hilbert space can be constructed or manufactured within if we define this integral in this way, and as a part of Lebesgue integration. And another popular definition which may be is that it's a finite dimensional coordinates is the space of all sequences. So Hilbert space is space of all those sequences, space of all those sequences zeta n's of numbers numbers. So numbers may be real or complex. So we normally are interested in complex Hilbert spaces, but we can complexify the real space also. And we can go from complex to real and real to complex. So, but to begin with, if Hilbert spaces are space of all sequence of numbers, whether real or complex, as the case may be, for which this square converges. So this is another way of defining. So spaces of all those sequences, zeta n numbers for which this the product of this square of this zeta n converges. So this is another way of defining the Hilbert space. So, but using completeness, we can discuss this convergence of some infinite. So the point is how we can define the convergences of. So it all comes. This boils down to how we can define convergence of infinite sums or sequences. You can say sequences. Sequences. Even though you can just do away with the difficulties of infinite dimensionality if you want to. So there are ways to do it, but the point is that there are some subtleties which come into making. So once we make it complete, once it's infinite dimensional, and we have also said we have to make it in a way which that things should be bounded above or below. So we have used this term. The Hilbert state is restricted by additional conditions whose purpose is to limit size of the space from both above and below. That's the thing. Now the point is, once we do unitary transformations, which we have been doing it throughout, and how we define, and we have some operations like that of isometry, and how we relate to Hilbert to normally how we relate to finite dimensional vector spaces. So the point, those very things, how we can complexify the things, how we have a, and how we can have an isometry vis-a-vis that finite dimensional vector spaces. So in this sense here we have an already an infinite dimensional vector space which is called Hilbert space, which is bounded, which is the way we have defined it, which is which is complete, sorry, it's completed, which is complete. So how we can do those operations, and what are the difficulties which come out? So for example, so we'll start to study orthogonal or unitary transformations. So we shall call a unitary transformation orthogonal. So we know unitary transformation has the property u star is 1 or u diagonal is 1, and we know size transformations are isometric. So that means modulus of ux can be modulus of x, or we can equivalently say u of x, u of y is, this is x and y. So if you define this way, so we can always construct an isometric transformation which is not unitary. So which is not unitary. So but so it's because of it. So now point is, why should we go to this thing? So we say that we construct a Hilbert space in which there are complete orthonormal set. So now what it has to do with the Hilbert spaces? Now if we define isometric operations this way, so the problem, so what is it? So now we consider a Hilbert space. We consider a Hilbert space. We consider a Hilbert space. We consider a Hilbert space in which there is a complete countable, in which there is countable complete orthonormal set, say for example, say orthonormal set x0, x1, x2. So a unique bounded linear transformation U is defined such that a bounded linear transformation can be defined by the conditions for n is equal to 0. So bounded linear transformation can be defined by these conditions, and which is isometric, having the property u star u is equal to 1. But since if you have an orthogonal transformation, then u star x naught will come out to be true, and that means this property is not satisfied. This unitary transformation is not satisfied for this orthogonal transformation. So what will it lead to? So if for an orthogonal transformation, this unitary property is not satisfied. So what it has to do with the Hilbert theorem? So the thing is that if you just recourse, we previously talked of something called a particular condition where the proper value may or may not come out to be 1. So if it doesn't come out to be 0, what is the solution to that thing? So if I'll just rehash what would say. So for example, the proper value, for example, the definition of proper value as a number lambda, for them there are solutions, ax is equal to lambda x, has a non-zero solutions, has non-zero solutions. Does it make sense about the reality of proper values of self-adjoint transformation being true? So the notion of proper values loses. Notion of proper value loses much of its sexuality. The notion of proper value is very much useful in the finite dimensional vector spaces, in the sense that if something goes wrong with a minus lambda, something goes wrong with a minus lambda, so the inverse refuses to x. Inverse refuses to exist. So essentially, different. So it is true for infinite dimensional cases, but different thing can happen for this is for finite dimensional cases, but for infinite dimensional cases, different things can exist. Possibilities exist because the inverse of a minus lambda may exist, but it can be unbounded. So it needs a bit of thinking what we mean by that. So for finite dimensional this vector spaces, the solution can have non-zero solution, and if it's zero, the notion of proper value loses sense in that sense. But for infinite dimensional vector spaces, or how we define Hilbert spaces, the solution may exist even though the inverse may refuse to exist, but it may be unbounded. But how we have defined this thing? It's Hilbert space is its completeness, so it can be bounded from above or below. So how we define this bound? How we can see the bound? So it is interesting, an interesting exercises which will not prove here, but will only state that for large class of unbounded transformations, large classes of unbounded transformations, it's found to be true, or it's found to be valid. Uh, so maybe there are maybe becomes more technical or going to levies, strictures, these conditions and other things. So the discussion. So I'll just maybe. So the thing is that the way we have used adjoint transformations in the finite dimensional Hilbert spaces, and we have used a spectral theorem where we can identify the particular solution to the that transformation. There is that the relation to that. So you can also use that spectral theorem within the context of this infinite dimensional Hilbert space or infinite dimensional vector space or what's Hilbert spaces. But there come out to be various subtleties or attached to it how we can do spectral theorem here also in that sense. And those properties which we have discussed there, like that of polar decomposition, if you remember, commutativity, and other things, they come out to be true here also, because the key difficulty here comes from the fact these which the transformations which may be non-normal, which are not normal transformations and which are unbounded. So it's also an exercise how we can prove spectral theorems for the infinite dimensional cases or Hilbert spaces, and prove the corresponding conditions or properties of these commutativity and other things. There may be subtleties which are attached to it. So then after that we do these things, so it will not be that difficult to show that self-adjoint linear transformations is defined for all vector space. So if we do all the things, so it may not be a difficult exercise to show that self-adjoint linear transformation defined for all vectors of defined for all vectors of Hilbert spaces is bounded on that side. So this was our discussion of this Hilbert spaces. But the point is that if you are maybe also physics students, the use of a Hilbert space is very much throughout the books of quantum mechanics. You can say and you can read. So use of Hilbert space is heavily used. So I'll just use one or two sentences. In quantum mechanics, what do we say in quantum mechanics? Quantum mechanics, quantum mechanics shows a physical system that's represented by vectors and Hilbert. Shows a physical system as a system represented by vectors. It's represented by vectors in Hilbert space. And in the context of Hilbert space, it shows it's an inner product space. Space which is infinite dimension. Which would have been, so it will naturally satisfy the condition, satisfy linearity based condition that we define a wave function psi. You might have seen it continuously in your books. We define it like this. And if sine phi are not, they are orthogonal, we say this is equal to 0. And so, and in quantum mechanics, we say that Hermitian operator is important to identify the positions of variables of position and velocity. And maybe these things will connect also something called L2 species, L2 Hilbert species. Yeah, Lebesgue integration L2 species, yeah, Lebesgue major is a word, proper word. Adjoint appropriators. So Hilbert space can also be related with the Euclidean space with an infinite series of points. So there is a connection of Hilbert space also with the Euclidean space. It's related with the infinite series of points only. Yes, yes, which may be tens. There's a discussion maybe of Hilbert space which is given in this Mathematical Foundations of Quantum Mechanics by one this chapter in that context. Initial days when quantum mechanics was evolving, how this clothing, this mathematical way of just clothing the quantum mechanics mathematical foundations of quantum mechanics in a mathematical way. There is an interest. This is an interesting chapter in the study of quantum mechanics. So maybe I'll stop here. So we have completed this finite dimensional, our account of finite dimensional Hilbert space. Thanks for being part of. If you have, if you are, thanks for what in whatever way you like for listening.